talking about special theory of relativity. Let's come to that. Hmm. So, special theory of relativity. So there was a scientist called Maxwell who said that light speed remains same for all, is irrespective of the observer. So that contradicted or opposed what the classical relativity said. So what was the solution? For many years the scientists couldn't find no answer, but the great scientist Albert Einstein gave the solution. That was the special theory of relativity. Now this too has two parts: time dilation and length contraction. So first let's talk about time dilation. Time dilation. Think of two mirrors. And think of this light beam that's going and getting reflective again and again. And there's one more set, identical set. This is case 1 and case 2. So think of it moving towards the right with the speed of light. You'll see yeah, that's it. So as the speed of light remains same for all, so it'll go back and it'll touch the bottom after the same amount of time. And for that to be possible, the time has to go slower for one. So think of it by the formula S is equal, speed is equal to distance upon time. So speed has to remain same for all. Now as you can see, the distance has increased. These two systems. This is clearly more than this one. So D is increasing. So for this to remain same, this S, take this as S naught. So this S naught, in this case, the T also has to increase so that this S remains same because D is increasing. So T2 has increased. That means that the time is moving slower in the case 1. This is called time dilation. And this has been proved by many experiments. So when we were experimenting, we saw that the time doesn't dilate much. So this was wrong then. So how is it correct? How it's correct? I'm going to tell you about that, and that's it's length contraction. So as I said, when we when, when experiments were carried out, we saw that time doesn't dilate much. So S is equal to d upon t, speed is equal to distance upon time. So we saw that time doesn't dilate much. So what could be the possible answer? If time doesn't dilate much, then d has to contract. I mean, consider back again the example. This was going like this. So while moving, this thing gets shorter. Yeah, this thing gets shorter, and this is length contraction. So I hope you got it. That's a bit tricky concept, and you can go back again and again to check the video because this it's not easy at all. It's not easy theory to grasp. So you can go back and check. There's no problem if you don't get it at once. So this was the special theory of relativity, and I'm going on to the general theory of relativity now. Hope you got it.